the metabolism pathway is you've got all of the details in the notes, but there will be some places where I say this is the key thing you want to get out of this process, because some of these have quite long metabolic pathways in there that you don't necessarily need to memorize all of the steps to them. If you have to memorize it in order for it to make sense to know the abbreviation, and that's just the way your brain works, I can't change that part for you, but I'm not going to test you on all of the little steps in between in there. It's more of what is the big picture, what are you getting from this process that's more important in there. So with cellular respiration, the name respiration got tied with it because of the link with breathing in there for aerobic metabolism. The term respiration is also used with the lungs, so it's kind of misleading when you look at it in there because not all of metabolism is going to involve oxygen. The name just stuck to call it respiration in there. But to call it metabolism is a much more descriptive name, a more accurate descriptive name in there. So you'll see both used. I tend to call it metabolism, but I'm trying with the book to stay consistent with their terms in there. So you may hear me just refer to it as metabolism in there because that is how I learned it, and it's what tends to stick for me. So with catabolism, these are the pathways that are going to break things down, and we've got multiple pathways that will do this. The reason we break things down is we're trying to free up that potential energy that is in the bonds of those molecules we're breaking down. So there's a few different processes that can happen. Fermentation is going to be one that degrades things partially. The other pathways degrade things all the way, but fermentation is partial, so there's still going to be some carbons left in the process. And this occurs without the use of oxygen. So we do some fermentation in some of our muscles when you produce lactic acid. A lot of bacteria are going to do fermentation in there. It's how alcohol is made, is fermentation. And that's the reason why you actually get alcohol, is some of the carbon is left in there to make the ethanol, which is the one that you usually are drinking. Aerobic respiration or metabolism is going to have oxygen consumed in there. And so cellular respiration is another term in there that is used that technically includes both aerobic and anaerobic processes, but it gets used as a synonym for the aerobic respiration. So what's going to happen in these processes is you're going to take some organic compound, and for what we study in here, it's usually a sugar. Most of the time glucose is going to be the pathway we look at. It gets combined with oxygen, and it gets broken down to release carbon dioxide, water, and energy. So if we look at it specifically with glucose, this is glucose here with the 6 carbons. It's going to take 6 oxygens. You'll get 6 carbon dioxide, 6 waters, and energy in the form of ATP and heat. So that is what you get out of the overall whole entire process. And it's going to have a negative delta G of 686 kilocalories per moles, which means it is spontaneous in there. So your catabolic pathways themselves are not actually going to perform the cellular work. What's going to happen is they're going to release energy, and you're going to store that energy in ATP. And then you can use the ATP to do work in other places. They say it acts like the chemical drive shaft. You can also think of it as you go to work and you get a paycheck, but they don't pay you with a bag of groceries and so much that you can use for your cell phone and so much on your electric bill. they pay you in dollars, and then you use the dollars to pay for those other things in there. So the ATP is like the dollars in there. So the reactions are what we call redox reactions, which means you're going to be doing some oxidation and some reduction, which happens by moving electrons. So when you are going to oxidize something, oxidation is the loss of an electron from one substance to another, and reduction is the gain of an electron from another substance. And we call them redox reactions because you're going to have these things occurring together most of the time. You can't gain an electron out of nowhere. You've got to get it from something else. So when you gain an electron to become reduced, something else has to become oxidized to give you the electron. So they just naturally occur together in there. So a reducing agent is going to be an electron donor because it donates an electron to reduce something else. And then the oxidizing agent is going to be an electron acceptor that oxidizes something else. So the way I remember what is reduced is when you reduce something, you're adding another electron on there. It's another negative charge. Another negative in there is actually a smaller number. You're reducing the whole number. That's what works for me to remember it. If you have some other technique that works for you, that's fine. So because of it requiring both the donor and acceptor, they're going to occur together. And so these are where I typed them in before I had the pictures in there and tried to create these lines. This picture works a lot better in there. So you've got here the carbon dioxide and the methane becoming oxidized, the oxygen and water becoming reduced in there. So what it means is while something in that reaction is oxidized, something else is going to be reduced. That's the key thing to remember, is that they occur together. I'm not going to ask you which thing is oxidized, which thing is reduced, which one is an oxidizing agent in there. Remember what it means to be oxidized, what it means to be reduced, and that's enough to keep straight in your head right now. So when you're reducing things and oxidizing things in there, you're going to have some potential energy that gets released along the way in there. So when we start to break things down, we are, rather than breaking things down in one giant step, we're going to break them down in multiple smaller steps. The reason for doing the multiple smaller steps is it's going to release energy in smaller amounts. So you can think of it as if you go to work, rather than them just paying you one big check at the end of the year, they pay you in smaller amounts, and it's easier to be able to take those smaller amounts and pay some bills here and there and divide it up, rather than to have to wait and pay it all at once at the end of the year. And so it's easier for the cell to take those smaller amounts of energy and direct them in different places than it is to get one big lump sum of energy and have to break it up to send it to different places in there. So one of the ways that we move electrons is through this molecule, this NAD. It's nicotinamide adenine dinucleotide. You don't need to worry about that real name of it. We always abbreviate it as NAD and NADH in there. And so it's one way that we can move electrons. So it can go between an oxidized and a reduced state. If it's got an electron, it's reduced. If it gives up the electron, it's oxidized. And it will accept and release that electron pretty readily, so it can be used to transport electrons in the metabolic processes in there. So in some of the key steps in there, as we break down glucose in there, we look at how electrons get moved around in some of those key steps. So some of this that is little details that I think probably actually make it more confusing, I'm going to just kind of brush over real quickly like that. So one of the reasons that NAD works really well in here is the downhill carrier is more electronegative than the uphill neighbor. So by being more electronegative, it's going to pull the electron harder than the one who had it. So if you keep passing it slowly down to more and more electronegative things in there, it helps to drive the reaction downhill in there. So this is just what an ATP or an NAD looks like on here, and just showing where you can have the hydrogens and the electrons go on and off of there. So you've got NAD plus and then you've got NADH in there. So NAD plus is when it's become oxidized, NADH is the reduced state. So this picture here is kind of a nice one to look back on. I would star that one in your notes, is when you're trying to go back and say, okay, where does this fit in the big picture? This is a nice picture to come back to look at for that. So where we're going to look at the processes is they start right here. This is the cytosol of your cell, and then you've got your mitochondria here. So glycolysis is going to be the first process. In glycolysis, you're going to go through 10 steps. They are going to split glucose in half to make pyruvate. And provided you have oxygen available, you're going to take that pyruvate and it gets converted to acetyl-CoA in the mitochondria. And then it's going to join in with this next cycle here called the citric acid cycle or Krebs cycle. It's also sometimes called the TCA cycle. We like to give things a lot of names apparently. And this is going to finish breaking it down. So in this state here with glycolysis, you're going to get some ATP out of that through substrate level phosphorylation. You don't get a lot, just a little bit of ATP. And you're going to move a few electrons through NADH. This is just kind of an intermediate step converting things to go into the citric acid cycle. Here you're going to make a little bit more ATP through substrate level phosphorylation, and you're going to move a lot more electrons through NADH and FADH2. That step is going to, or that particular cycle is going to generate most of its energy by moving those electrons. So since the way we like to use energy in the cell is through ATP, the electron transport chain is going to help with transporting and converting these electron carriers in there through chemiosmosis to make ATP at the end. So it's kind of where you do your conversion. So if you think of it as this being like getting paid in pesos and euros, they're still an energy currency, but they're not the ones you want to use. If you go to the grocery store, even with Canadian dollars here, they're going to look at you and be like, are you crazy? Never mind the fact that Canada is happy to take our money while you're there. But here we would go, no, we don't want that Canadian money. Go get it exchanged. And this is going to be where you go get it exchanged to get the money you do want out the other side. So when you're looking at this, the way I'm going to recommend you guys study this is take one pathway at a time, spend no more than 20 minutes with the thing, because after that you're just beating your head against the wall. Try and understand one pathway, come back and look and see where it fits in the big picture. Go do something else for a little while, let your brain rest, and then look at another pathway in there. If you can only look at part of a pathway in that 20 minutes, that's fine. Just take it in small bites rather than trying to get the whole big picture in one sitting. It doesn't work well for many people that way. So this picture here is illustrating that where you take your energy from this, where you start out with this huge amount of energy that's going to be released by moving those electrons in those redox reactions. But what we're going to do is it's going to go down some steps in there so that we don't end up with a huge explosive reaction in there, but you actually get smaller amounts of energy in usable amounts. So this is that big once a year paycheck. This is the every 2 weeks paycheck. So with the phosphorylation in there, you'll see substrate level and the oxidative phosphorylation in there. Substrate level means that it's coming off of another phosphate group is coming off of another organic substance, is where it comes from. When you do oxidative phosphorylation, it's going to come from an inorganic phosphate. So it's just two different sources of it in there. They talk about that. It's noted in there how you get the different levels of phosphorylation. Honestly, right now, is it going to make a difference in how you understand it on whether it's substrate level or oxidative phosphorylation? No. You just be aware that is out there, but I'm not going to ask you the difference in those. It's phosphorylated. The end result is the same thing in there. So when we go through and do this, for each glucose that is oxidized to carbon dioxide with respiration, you get about 38 ATP. You have to put 2 ATP into the deal to get it started. So we say you have a net gain of 36 ATP or 73 kilocalories per mole of free energy formed in there. So there is a little bit of variation in that. It depends if sometimes you don't completely break things down. As you're going down that pathway for metabolism, some of those things can be building blocks to make something else. If you need one of those building blocks and you pull it out of that pathway, that particular glucose isn't going to end up giving you all of that energy in there. So that's why we say it's an approximate in there, because not all of them will always go through that pathway. That's more of just a reality of the situation. The way they tend to look at it for test questions on things as if every glucose completely goes through the pathway. So with glycolysis, the name literally means to lyse glucose in there. So if you lyse something, you're going to split it, and you're going to split it in half here. This is a good summary of what happens in glycolysis. You start with glucose that is going to have 6 carbons in it. And if you look at it in terms of keeping track of the carbons, that can be helpful too, because carbons aren't going to just disappear into nowhere. They all have to be accounted for. So you start out with the glucose, and you want to basically burn this and get it going. If you want to burn a fire, you don't just look at it and say, burn. You've got to put some energy into it. And so you can think of this being like lighting your matches to get some ATP into it, to get that fire going. So that is your energy investment phase. Once the fire gets going in there, you're going to have the energy payoff phase, where now you're going to form some ATP. You're going to get some of that energy back that you had to invest in there. You also move around some electrons and get some NADH in there. So it takes 2 to get it started. You get 4 out. What you end up with in the end is a net of 2 ATP gained in glycolysis. You take that glucose and you've split it in half to make 2 pyruvates. Glucose has 6 carbons. Each pyruvate has 3. So all of the carbons are still accounted for. And you move some electrons on there and get some NADH. So this is a wordy description in here of what is happening in this picture. Like I said, if you have to look and memorize all of these steps to make sense of that, that is your own brain's issue that I cannot change for you. That's what I had to do to make sense of this thing. And I mean, it was like beating it into my head. And once I said, okay, I can't just remember these little short steps in there. I have to sit down and understand how everything goes. Then it wasn't so bad to learn this. So basically it starts out with your glucose here that has 6 carbons in it. And what this shows is that first match that you light. So if you make a campfire, you put in 1 match and it starts to burn a little bit, but a lot of times it's not enough to really light that fire. You have to put in more, and that's where the second ATP comes in, where you have to give it a little bit more energy. If you look at here, where you can see in yellow, you've taken the 1-phosphate off of the ATP, which is adenosine triphosphate, meaning 3. Now you're down to adenosine diphosphate, which is 2. That 3rd phosphate got stuck on the glucose. And what this name means here with glucose 6-phosphate is you put that phosphate on carbon number 6. So that's all that name means. When you go from glucose to fructose, it just means you've rearranged it a little bit in there. And when you add in another phosphate to get that fire going here, you get fructose 1,6-bisphosphate. Bis is because there's 2 of them. In chemistry, they'll either use bis or diphosphate. They mean the same thing, so the terms would be interchangeable. You may see fructose 1,6-diphosphate in another source, and it's correct too. So it just means that the phosphate is on carbon number 1 and carbon number 6 here. These are the enzymes that are going to control each one in there. In biochemistry, it would be something that you would need to know the enzymes. I'm not concerned about you knowing them, but one thing that is interesting to know, enzymes usually have cofactors. Any idea what would be your cofactor or coenzymes in these reactions? What is your most common ones? So most of these for metabolism are going to use your B vitamins as your cofactors in there. So sometimes you'll hear people say, well, I started taking vitamins and they just gave me so much more energy. The vitamin itself doesn't have any energy in there to give you. It's not broken down in that way. What the vitamin does is it helps to allow these reactions to take place in there. So if you don't have the coenzyme that's needed, the enzyme doesn't work anymore. So it allows you to harvest the energy from something else, is what it does. It doesn't actually give you the energy itself. So if you don't need any more, if you have all the enzyme you need in there, taking a vitamin isn't going to give you any more if you already have all you need. It's only going to make you feel more energy if you are short on the cofactor in there, is the only way it would give you more energy. And vitamins can be found in your fresh fruits and vegetables, are going to have a lot of them. So when we get to this fructose 1,6-bisphosphate here, we're going to split this, and it makes this dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. What's going to happen is this piece here is going to continue on to the next step, and these two are interchangeable. Because it likes to be in equilibrium, if you keep taking one side of the pile and it keeps wanting it to be equal, it's going to always shift this over to can get converted into this. A lot of times they don't even show this step here because these all are going to get converted to here. So those are your energy investment reactions in there. So in your energy payoff phase here, this is going to show where you're going to take that from up here, the glyceraldehyde 3-phosphate. In here, it's going to have another phosphate come in, an inorganic phosphate that gets added on, and you're going to make 1,3-bisphosphoglycerate. So phosphates on carbon 1 and 3. And right here is where we're finally going to get some of the energy back in there. So the phosphates get pulled off. They get put back on the ADPs to make triphosphate again in there. So in this step here, you're going to get 2 ATP back. Remember, you've split it in half, so you've got 2 of those molecules coming through there. That's why you're getting 2 ATP back. And your fire continues to burn, rearranges a little bit. So just like when you make a campfire, as the wood starts to burn and the pieces get smaller and break down, it starts to kind of shift and make a smaller pile. That's what this is doing, is it's just shifting around in there. So you got a 3-phosphoglycerate, 2-phosphoglycerate, phosphoenolpyruvate, and we're going to pull off the last 2 phosphates in there to make 2 more ATP, and you get pyruvate at the end, which has 3 carbons. So it makes sense to follow it on the paper. Not necessarily to reproduce it, but you could look at that and say, okay, I can look and watch where the phosphates go. I can see that we start with 6 carbons at the beginning. I can see why we still have 6 carbons at the end. I'm not worried about you memorizing the names in between. What you will want to know is the name of what starts, the name of what finishes, how many ATP you get out of the deal. Fraction of a second. It depends on what your energy need is. If you are not using a lot of energy, your body is not going to do a lot of these cycles. It's more of how many times are you going to be doing this, how many of these are going to be going on at the same time in there. So when you need more energy, you'll have more of it going on at the same time. When you don't need more energy, what happens if you have glucose is it goes through here, and instead of going on to the next step of completely breaking it down, it just goes into the fat storage step. And it doesn't take much energy to do that one. So if you look back on this picture here, if you can understand and go, okay, this makes sense to me how we go through all of these things without having to say all the steps in between, that's a good place to be with this. So in that first cycle of glycolysis, you'll notice we didn't talk about oxygen interacting in there at all. That one will occur whether oxygen is present or not in there. So if you are doing anaerobic activity where your muscles, you're sprinting and you're going as hard as you can, yeah, some of your muscles are getting oxygen, but they're not getting as much as they need. The ones that aren't getting oxygen are going to have to rely on that for their energy source. And 2 ATP is just not very much energy. It's not enough to really, it will allow one fiber to pull on another in a muscle and release one time. That's not enough to even contract a whole muscle cell. It will contract a portion of a muscle cell. So it's a really small amount. So if we have oxygen present, now we're going to look at what happens to the pyruvate. And it's going to go into that citric acid cycle or Krebs cycle in there. And this is going to complete the oxidation. So you take your pyruvate here, and it's going to get converted to acetyl-CoA. Acetyl-CoA only has 2 carbons. So this step is irreversible because as you do this, you're going to pull off carbon dioxide. Any idea what happens to that carbon dioxide? You're going to exhale it. So even if you exhale it into a bag and you suck it back in, you don't have the enzymes to glue this together unless you are a plant. So once this is off of here, you are committed to this pathway here. That becomes significant later on when you look at which nutrients can you convert back into sugar to fuel the brain. If it's on the far side of this, it can't be converted back into sugar. Before this step, you can convert things back into sugar because of this step being irreversible in there. You're also going to move some electrons when you do this so that you're going to make another NADH here. That NADH is kind of like if you done a little bit of work in Canada and they gave you your Canadian dollars, you just kind of go, okay, let's stick it in my pocket and I'll deal with converting that money later. So again, this is word descriptions of what we're going to go through on here. So you've got this acetyl-CoA that's got 2 carbons here. It's going to get joined with this oxaloacetate that you had left over from the last time this cycle happened. Oxaloacetate has 4 carbons. So you're going to take those 4 carbons plus these 2 carbons and you're going to make citrate that has 6 carbons. It's just a Krebs cycle intermediate in there. The names come from how many carbons they have and their arrangement in there. So it's a chemical. I know that's not really helping you a lot in there, but there isn't much more to describe it as. So if you think of it, your 4 carbons plus your 2 carbons, you make this citrate 6 carbons. So sometimes you'll see when you take certain vitamins or minerals that it will say it's chelated to citrate and they're bound to citrate. The idea is that that citrate is something you naturally incorporate into this cycle, that you could absorb that mineral into that cycle where you need it for a cofactor or a coenzyme more readily. And so we need to be able to completely break down the other 2 carbons. We've already exhaled one of them as carbon dioxide, and when we looked at that reaction at the start, you made 6 carbon dioxides in there. So you've had the one that's broken off, and you had 2 of those molecules, 2 pyruvates that got converted to acetyl-CoA. So there's 2 carbon dioxides that are made. We're going to need to get rid of the other carbon dioxides as we go. So this citrate gets rearranged to isocitrate. When you see the iso on there, it means it's a rearranged chemical. And then we're going to move some more electrons to get this NADH, so some energy is released in here. We're going to pull off another carbon here, so now we're going to be down to 5 carbons in alpha-ketoglutarate. So again, we're going to pull off another carbon, and it has to combine with oxygen like this one did in there. It's going to have some more electrons be released in there. So now we're down to 4 carbons in this succinyl-CoA. So considering you've got 2 turns of this cycle for each glucose, now you had your first 2 when you made the acetyl-CoA. Here's the next 2 carbons gone. Here is the next 2 carbons gone. So at that point, all 6 carbons from your glucose have now been turned into carbon dioxide. So right here, you can see the carbon is in blue because it came from here. The O2 oxygen that you're going to inhale from the environment is what's used to join that. So if you don't have the oxygen to combine this to, you don't take that next step. So it's never going to go and just say, well, I'm going to exhale just a carbon by itself and not put it with anything. It'll just stop there. What will happen is it will start to do more glycolysis to get the energy. Either that or the system's just going to fail and you're not going to have the energy to do it anymore. So the process will stop. If you're looking at it in a muscle, when that happens, that's when it fatigues and it just says, you know what, I can't do it anymore, and it won't contract anymore. So these, again, are going to be exhaled. So they're irreversible steps because you can't glue those back on. So we're going to continue to rearrange this. And so like that fire where the logs are rearranging and it's kind of shifting down, it does continue to release some energy in there. So when you go from succinyl-CoA to succinate, it's going to release some energy in the form of GTP from GDP. And it just uses a different molecule to hold on to the phosphates. And then when it does that, it's going to transfer them on to ATP again. So this GTP is going to make a direct conversion to some more ATP. The succinate's going to continue to release energy, and it will shift down to make the fumarate. And it's going to move some more electrons in the form of taking FAD to FADH2. And then the fumarate gets converted into malate, and the malate will get converted into oxaloacetate. In that step, it's going to release some more electrons. And that oxaloacetate is ready to take the next acetyl-CoA that comes in. So if you don't have oxygen, cycle doesn't want to spin in there. You've probably heard that you have to have oxygen to burn fat. Where fats come into the mix is at the acetyl-CoA. And so if you're not doing this in here to use up those acetyl-CoAs, you're not going to use up the fat. Your body will just store it in there. Likewise, if you don't, well, you do produce some water. If you don't have adequate water to put into some of these steps, that process isn't going to happen either. So you need to have all of the materials in here. The body doesn't look at it and say, well, you know what, I want chocolate chip cookies with walnuts, but I don't have any walnuts today, so I'm just going to make them with chocolate chips and those will be good enough. It doesn't do that. It's going to say, no walnuts, I'm not making them. No budging on there. You give me all the tools I need or I'm not doing the job, period. So does it make sense to look at this and you can see and go, okay, I see where I put in 2 carbons, where they come out, and that the cycle feeds itself again when you look at it? Any questions on that part? Okay, so now we need to look at what happens to all of those FADH2s and NADHs. So this process of the Krebs cycle has occurred in the mitochondria, so we're already at that area. In the mitochondria and the membrane, you've got this electron transport chain, which is going to be a collection of molecules that are embedded in the membrane in there. If you're a prokaryote, you're going to have this in your cell membrane instead. And there are multi-protein complexes, numbered 1 through 4 on here. And they're going to have these other prosthetic groups on there that are going to have components of catalytic enzymes. So like in protein 1 here, you've got flavomononucleotide, which is what the FMN stands for. So any idea what vitamin you might need to make this? So there's one called riboflavin in there. It's one of the B vitamins. That's where it ends up being used for. Another thing that you know you probably need to have in your diet is iron in there. So what happens when people don't have iron? What do they feel like? So what does it feel like to be anemic? Tired. So anemic because you can't transport the oxygen in the blood that you need for this cycle, but also you're not going to be good at converting these NADHs and FADH2s because you don't have the iron that you need for here. So it's one of those things. If you don't have all the tools, it refuses to work. And it's got sulfur in there. So sulfur is another nutrient you need. It's just a little bit more widespread. It doesn't, iron is more limited in its supply in your diet is why that tends to be more of a problem in there. And then you've got these cytochromes in there, which are going to be pigments that are going to help to move the electrons. So what the NADH is going to do is it picked up electrons earlier in the cycle. It's going to drop off its electrons here to the FMN. FADH2 picked up electrons too. It's going to drop off its electrons here at the iron sulfide in complex number 2. So they have different drop-off points where they're going to drop off their electrons. And these electrons are going to get passed down the line. You can see the little arrows on here. This is how you're going to pass the electrons down the chain. So it's kind of like having those stairs that the water is going to flow down the stairs in here. The electrons are going to flow down the stairs. When they get to the end of the stairs, those electrons are going to combine with some hydrogen ions and some more oxygen. So again, if you don't have the oxygen, you aren't going to do it, to make water. So this last step right here is what we're going to look at now. You have an enzyme that's going to allow that to happen called ATP synthase. It's sometimes called ATPase too in there. And so this is your membrane here, and this is that last step here where you've got this ATPase. And it's sometimes referred to as a proton pump. And they've looked at this and they've realized it actually moves like a rotor and stator from a motor in there. You've got this part here, the rotor, that actually spins. The electrons get dropped in. It spins around, and then it gets dropped into another little slot, and it's going to get dropped out there, or it's your hydrogen ions in there. And that's going to cause this part here to spin. So like with a motor where you have the inside spinning in there, if you're looking at it to be a generator to generate energy in there, it's going to generate the energy to take and connect that inorganic phosphate onto ADP to make ATP. So it's only been fairly recently that they've realized this structure actually works this way with the spinning to generate the energy. So now they're looking at that and going, well, how could we take this in the cells and somehow use that as a source to make energy to drive other things in the environment in there. So when it does this and it passes things down, because the NADH is going to drop off its electrons earlier, it's got more pathway to fall down. So more energy is released. If you look at it and you had a ball that you were going to roll from the top of the hill down and the one from the middle of the hill down, which one's going to have more kinetic energy as it rolls down? The one that comes from the top. Same thing with this. Because it's moving the electrons farther down the hill, the NADH is going to give more energy. So it will make about 3 ATP. FADH2, because it cheats and only goes partway up the hill to drop its ball, it's only going to give you 2 ATP. So when you look at the electron transport chain, what ends up happening is you have 6 NADH that get put in there from each glucose. You get 2 FADH2 from each glucose. And you'll get between 32 and 34 ATP, depending on how it decides to shuttle the electrons in there. 34 is the number that's used more commonly in there. When you're looking at standardized tests in there, what I would say is learn this 34 number in there, and then just know that sometimes it's not as efficient. So what you want to be able to do, what's sometimes helpful at home, is to look at it and you go, okay, I can start from the beginning with glucose and look and see, okay, here is where all of the NADHs come from. Here's where all the ATPs come from in there. I can see where all the FADH2s come from. I can see where all the carbons end up, where all the carbon dioxides go in there, and follow them through and figure out exactly how many, with the conversions in there, that you get 3 ATP for each of these, and come up with your total number. And if you can look through and track to get the total number in there, you know you're able to follow the pathway. So you notice I'm saying be able to follow it on paper, not necessarily reproduce it out of nowhere in your head. So what you're going to really want to know out of this pathway here, this ATP synthase in there, and the chemiosmosis. This term of it being a proton motive force in there, basically what's helping to drive them to want to go in that direction is that you've got protons and electrons separated. They want to come together. They want to go through this pump in there, and that's what's helping to generate that force. And then your conversion in there, the NADH giving you 3, the FADH giving you 2. So then this is a summary here of the whole cycle. So your complete oxidation of glucose under standard conditions is going to have a negative delta G of negative 686 in there. And your phosphorylation of ADP to ATP is going to take 7.3 kilocalories per mole. So if we want to look at how efficient is respiration in there, how much energy is being used versus how much you're getting out of it in there, you can calculate this in here. Again, that's not what I'm interested in you being able to do. But what that shows you that about 40% of the potential energy in glucose gets transferred to ATP under laboratory conditions. Under cellular conditions, inside your cell is actually the more ideal conditions for this to happen. It becomes more efficient in there, and so you get even more energy out of it in the cell. And even at 40%, that's still really efficient. They figure the most efficient car is still only going to convert about 25% of the energy into actual energy of making the car travel. So let's go ahead and take a break for a few minutes before we go into fermentation. I'm being sarcastic there. Yeah, it's like I said, don't worry about memorizing the names of the intermediates. If you have to take biochemistry at some point, you'll have to memorize them there. But the bigger picture of how you get the energy from it is what you want to know. So that's the aerobic metabolism. So now what we're going to look at is fermentation and your anaerobic respiration. So glycolysis is anaerobic. It doesn't need oxygen to happen. It's how you get things started. But when we look at what are we going to do with the rest of it in there when you get to acetyl-CoA and can't do anything else with it, this is where fermentation is going to come in. There are lots of different types of fermentation out there. There are lots of types of metabolism out there. This is probably the most common one of organisms we know. But to give you an idea, just in bacteria alone at the UW, I had to take a 5-credit class on different metabolic cycles of different bacteria. And every day we talked about at least one different metabolic cycle in there that was a whole new pathway for the bacteria in there. So they will basically eat anything and make all kinds of stuff. There isn't really any kind of substance that there isn't something that eats it out there. But this is the more common one. So with fermentation, this is going to get the chemical energy out of something without the use of oxygen and without the use of an electron transport chain. When you look at what defines it, no electron transport chain and no oxygen is going to be the key definition of it. You can actually have electron transport chains that are different than the one that we looked at on here. What fermentation is going to rely on is needing a sufficient supply of NADH to accept the electrons in there. That's what's going to be the limiting factor, is that oxidation and reduction. You got to have some place to put those electrons that you're pulling off. So with types of fermentation, alcohol fermentation, the pyruvate is going to release carbon dioxide to make acetaldehyde, and that gets reduced to NADH, or reduced by NADH to make ethanol, and helps to regenerate the supply of NAD plus to come from glycolysis. So what's going to happen is in glycolysis, you're going to make some NADH that you're going to use in alcohol fermentation. Then that NADH gets converted back to NAD plus that you use in glycolysis. So glycolysis, if you're not going to get rid of the stuff into aerobic metabolism, it needs fermentation to be able to continue on to. So the alcohol fermentation, this does not happen in humans. This would be more of a bacterial thing in there. So that's why you use bacteria or some yeast to make alcohol. Ethanol is the alcohol that is consumed in drinks. Lactic acid fermentation, this is going to be more of what goes on in an animal cell, meaning human cells in there. So your pyruvate gets reduced by NADH to form lactate. This time there's no release of carbon dioxide. The lactic acid is thought to contribute to muscle fatigue. That idea, they used to look at it and say, oh, building up the lactic acid, that's what gives you the delayed onset muscle soreness. We haven't ruled out that it might not be a contributor, but it's not the primary source for the muscle soreness in there. We know that you can pretty much clear the lactic acid much quicker than the 2 or 3 days that the muscles are sore in there. The lactic acid's cleared out of there a lot quicker. The muscle soreness is likely due to changes in the potassium level, as well as microtraumas that you do to the muscle in there, and the inflammation in there of trying to repair the muscle, not so much the lactic acid. The lactic acid actually helps you get more oxygen into your muscles. It lowers the pH so that you release the oxygen more readily in there. So the lactate can be converted back to pyruvate by the liver cells. So this lactic acid, if you want to keep it around as long as possible in your muscles, sit and do nothing. If you want to get rid of it faster, doing some easy activity in there so that your body needs to use more pyruvate again will help speed up the process in there. So the liver and muscle are going to be places where you can actually regenerate some of the energy out of there. So this is just a picture of it in there. The main thing to know is that you start with your pyruvate and you're either going to make lactate or ethanol with these cycles, that it's going to be dependent on the NADH moving the electrons. So when we compare aerobic respiration and fermentation in here, what you start out with is glycolysis is going to be the common precursor pathway to both of them. You're not going to choose fermentation or aerobic respiration until after you get to pyruvate. So when you get to pyruvate, if no oxygen is present or not enough oxygen is present, you'll make either ethanol or lactate in there depending on what organism you are. If there is oxygen present, then you'll make the acetyl-CoA and go into the citric acid cycle and the electron transport chain. So when you're doing an activity, say you're out going for a jog, you're going to be doing this pathway, but if you start to speed up in there, you're still going to be doing this pathway, but the extra energy you need that you're not able to get from this because you don't have enough oxygen is going to come from one of these pathways. So right now, your body's going to choose the most efficient pathway it has. It is this pathway here. It's just doing it really slowly. When you exercise, you speed up how quickly the pathway goes through. So other differences in there, the NADH gets oxidized back to NAD plus to sustain glycolysis. In fermentation, your final electron acceptor is an organic molecule. So you make, your end product is lactic acid or acetaldehyde for alcohol in there. In aerobic respiration, your final electron acceptor is oxygen. In aerobic respiration, you get a lot more ATP. You only get 2 from fermentation. So aerobic respiration is going to give you 19 times more ATP than fermentation in there. So if you have to choose a metabolic cycle, aerobic respiration is your one that's far more efficient. So when we look at the types of aerobic or oxygen users, we've got some different categories here. An obligate anaerobe can only do fermentation. They have to be in an anaerobic environment. They can't survive in oxygen. So they are an organism that oxygen is going to be toxic to them. They don't have a way of handling it, so it will kill them. Obligate aerobes only do aerobic respiration, but not fermentation. So the vertebrate brain is one of those. That would be your brain in there. It has to do aerobic metabolism in there. And it needs to metabolize glucose. So before you take a test, it's always a good idea to give your brain some glucose in there. Some people will go, well, I ate a lot of protein in there. Protein's not what your brain wants to use for energy. A lot of it comes in past the acetyl-CoA. You can't reverse it back up to make glucose out of it. So it's kind of like saying I'm going to hold my breath the whole time I take a test. It's not really helping your brain any. I had a student that I had a class that was like 4 o'clock in the afternoon, and he would be here all day long and not eat anything. And he was like, I can't concentrate on my tests. And I said, why don't you try eating something before you take the test? Eat a couple pieces of fruit or something. So he started eating 2 bananas before he was taking the test, and he got an A on every test afterwards. So, I mean, it really did make a huge difference for him. in there. And you may have had that experience yourself where maybe later in the day you have to make a decision and you're like, I just can't concentrate. And I know myself, if I need to have more sugar for my brain, I will get a little grumpy. Probably more than a little if you ask other people. And I feel a lot better if I go and eat something in there. So your facultative anaerobes, these can make enough ATP to survive using either fermentation or respiration. Mussels are going to fall into this category. If oxygen isn't available, they'll do glycolysis to work, but they would much rather use oxygen in there. So the evolutionary significance of glycolysis, it's thought that your ancient prokaryotes probably used glycolysis to make ATP before oxygen was present in the atmosphere. When you had the cyanobacteria produce oxygen gas as a byproduct of photosynthesis, then we started to build up more oxygen in the atmosphere, and that's what allowed them to be able to use oxygen later on in those pathways. So one of the things, you've got this main pathway that we've talked about, glycolysis in there for starting from glucose. However, you're going to eat things other than glucose. When you eat other sugars, they are going to get converted into glucose and join into glycolysis in there. When you eat proteins, they have to get broken down into the amino acids. The body's preference is to use proteins to rebuild structures. That's what they're meant to do. So the amount of protein intake you need really depends on your activity level and how much muscle growth you're doing. As an adult especially. As an adult, you're not getting taller. You're not going to, grow another 6 inches this year. Puberty is done. So that's not going to be your excuse. If you're completely sedentary, it doesn't take a whole lot of protein to maintain you. If you are a bodybuilder that's trying to build more muscle, it's going to take more protein in there to maintain those muscles and also to be able to build them. Excess amino acids, some of them can go into glycolysis and the citric acid cycle, but not all of them. Then you have your nitrogen waste that you have to remove in the form of ammonia and urea. So then you're going to have to put more work on the kidneys to get rid of that in there. So somebody who has kidney stones, a high protein diet is just egging on those kidney stones to come in. Your triglycerides, these are the fats you're going to consume. They're going to get broken down into glycerol and fatty acids. The glycerol is going to come in, and this picture here shows these. So your fatty acid, or your triglycerides here, your fats. Glycerol will come into glycolysis, so it can be converted back into sugars or go this way. Your fatty acids have to come in at acetyl-CoA. So if you have too many fatty acids in here, what they do is they just go back to storage. And it doesn't take much energy to convert them into storage. So one of the reasons why fats have so many calories is you do what we call beta oxidation in there. You split off 2 carbons at a time. A fatty acid that a human would eat is going to have between 16 and 18 carbons on it. So if you pull off 2 carbons at a time to make acetyl-CoA, you're going to make 8 or 9 acetyl-CoAs from every one of those. That means going through this cycle 8 or 9 times. From glucose, you only have to go through it twice. What's going to happen is your body's going to look and say, all right, we don't need to keep going through this cycle in here because we've gotten so much more ATP out of it. Once you don't need the ATP anymore, it just sends it back this way. And there should be another arrow here that just goes right to fat storage in there. So with your amino acids, some of them can come in here, some can come in and get used here, some get used here. But what happens if you eat too many proteins? This pathway here gets to go in reverse, and you can store that. So a lot of times people are under the impression that, well, I can eat as much protein as I want. Yeah, that's a lot of a nitrogen waste you have to get rid of. So you'll build up more ketones in there. Yeah. Oh, okay. But yeah, a lot of times people go, well, I'm not going to gain weight because I just ate all that extra protein. It is still too much. I mean, and I have a test question that I'll use in my one other class. And I'll say, what happens to excess amino acids in your diet? And everybody always picks, they get converted into muscles. And I'm like, really? You think the bodybuilder ate his way there? Why don't you look that way from eating? That's not what happens. This is the pathway. Too much of this over here. So, you know, there's a lot of diet fads out there that will say, oh, you get to eat as much as you want of this. You don't get to eat as much as you want of anything. The low-carb diets really try and say that is, oh, you can eat as much as you want of this. No, you can't. There's still a reason 68% of adults in this country are obese. Not just fat, obese. It all turns into this. You don't get to eat as much as you want of anything. So, anabolism in here. So when you want to make things in your body, sometimes you'll use the carbon skeletons out of that pathway. So things may only get partway down the pathway, and you may say, you know what, I need that glyceraldehyde 3-phosphate to make something. And the body will take those to make things. You'll use the amino acids to make your own proteins in there when you need to. Some of the intermediates from the citric acid cycle in glycolysis can be diverted into other pathways. But excess of everything all gets converted into fat. So the pathway gets regulated through feedback in there. Most common way is feedback inhibition, where when you start to have the end product of the pathway build up, you're going to start to inhibit the enzyme so you don't make it anymore. Catabolism is largely regulated with negative feedback levels in there. So if you start to have too much ATP in there, your body's going to say, okay, let's slow down the Krebs cycle here and just turn this into fat. So unless you're using up the ATP, your body's not going to just keep going on that cycle. It's going to say, turn it into fat. That's the main point you want to know out of that. So that is the end of metabolism on here.